Alright, silly people, here's the situation. Griffiths is asking us if the rows and columns of a unitary matrix, being one that has the property of its Hermitian conjugate equal to its inverse, are the rows and columns of that equal to some kind of orthonormal set? Um, and so this is a really loaded question, but we have to start by knowing what we're looking for, right? Um, let's say we have a vector um, A and a vector B. Both of them can be indexed by some letter J. Um, and then we know how dot products work, or inner products specifically. Um, if you wanted to take the inner product of A with B, you'd take the sum of J all the way until you get to however many components A and B have of A star J B sub J, right? That's how dot products work. You just index the same elements of either and you multiply them and you sum together the products. The thing is that for orthonormal sets, if it is truly orthonormal, this is only going to have one result. It's either going to be 0 or 1 if orthonormal, which just means that they're either completely perpendicular to each other and therefore the dot product is 0, or they're identical and so the dot product is 1. So if A and B are like this, then they form an orthonormal set, right? Cool. Back to the unitary matrix thing. U dagger equals U inverse, that's cool, but another way to write that is that U times U dagger is equal to the identity matrix, because the U dagger will be equal to its inverse. So the product of the two will be the identity matrix. And then Griffiths had a way of writing the identity matrix in the chapter where he actually indexed it with a delta sub ik. That's called a Kronecker delta. It has the property of it being 0 if I is not equal to k, and 1 if I equals k. So you can already kind of tell we're on the right track because we have zeros and ones again. But that's cool. But also, like, we have a formula for multiplying two matrices together that Griffiths has given us. We know that another sum over j n components, but we just multiply u sub ij with u j k, and then you index whatever matrices are in the product. And that's why I use the symbols ik, so I can just directly use that formula. But we know how to do a Hermitian conjugate actually, because it's just a transpose followed by a complex conjugate. So we know that u sub jk dagger is actually just u kj complex conjugate. And this is really interesting now. So it looks like we have a complex vector being indexed j, like here, and we've got a vector here that is also being indexed j, and we have on the right hand side a 0 and a 1. So that's awesome. How do we interpret that? Well, so the way to interpret these is you have u sub ij, if you were to actually write u in matrix notation. I is the row, so you have something on the ith row, and j represents the column, so this is j equals 1, j equals 2, j equals 3, so on. And so it has these components: u sub I1, u sub I2, u sub I3, dot dot dot. But then we also have this u sub kj. That's just going to be a different row than the kth row. And it has these components, u sub k1, u sub k2, u sub k3, dot, dot, dot. But whenever we're in the dot product, we're taking the complex conjugate of them, of course. But so yeah, we're basically getting that if we treat the kth row as A and the ith row as B and index them J and multiply them together, you get that they're an orthonormal set. So that's pretty funny stuff.